Hey guys, in this lecture we're going to get into carbohydrates, which is the first of the four major categories of organic compounds. Within this discussion we're going to talk about the basic components of the concept of one compared to many, which is the monomer compared to the polymer, which is something we'll reiterate and come back to for all organic compounds. Then specifically we'll talk about carbohydrates monomer, which is the monosaccharide, then talk about its polymer, which is the polysaccharide, and then kind of bring it all together in terms of how each can be developed from the other, how polysaccharides can be made through something called dehydration synthesis, and then the polysaccharides can be broken into monosaccharides again through the process of hydrolysis. So first, before we get into any of the specifics on carbohydrates, let's first talk about the concept of a monomer versus a polymer. Now, if you know anything about kind of prefixes and their origins from different languages, usually Latin or Greek based, the prefix mono means one or singular, right? Whereas the prefix poly means many. So if I refer to something as a monomer, then I mean that it's a single piece by itself. So I have a picture here of single pieces of Legos. So imagine a single piece of Lego as a monomer. So you have a single piece by itself. Can't really do much with it. You can't really make much with it unless you have some sort of really creative imagination. But if you want to actually put something together, you're going to need to take many separate pieces and put them together in some sort of an organized form. So if we think of the single Lego piece as the monomer, then the polymer would be multiple Lego pieces combined to actually form some sort of a structure. So when we refer to the terms monomer and polymer for all categories of organic compounds, I want you to think of the monomer as the single piece by itself. Oftentimes we refer to it as the building block, and then the polymer would be many monomers combined together in a form that is structurally successful. Okay? So before we get into the specifics on the monomer and polymer of carbohydrates, let's first focus in on an understanding of its major function. And to really do that, I'm going to tell you a little story. I'm going to get a little personal with you guys here. My wife and I got married, and we went on an amazing honeymoon through Europe. And while we were there, we went to Paris. That's my wife. She's gorgeous. I know what you're thinking, right? Yes, thank you very much. She is beautiful. We went through Paris, had a beautiful time, enjoyed France very much. Then we went through Spain. When we were in Spain, we went to Ibiza, which is a beautiful island off the coast of Spain, and we went to Barcelona, which again is amazing, right? And then after we went through Spain, we then took a detour and went off into Germany, and we spent some time in Munich out in Germany. And again, every single part of the trip was fascinating, really gorgeous memories that I'll never ever forget. But the reason I'm telling you guys this story is because while we were through Europe, we had two forms of currency with us throughout the whole time. We had dollars and we had euros. Okay? So if I have both dollars and euros and I'm traveling through Europe, which of the two do you think we used first? Exactly, the euros, right? Why would we use euros? Again, yeah, exactly. You can't use dollars when you're going through these countries in Europe. They don't accept dollars. So if we wanted to purchase anything for any given reason, food, gifts, whatever, we had to pay in the form of currency that they readily accepted. So because we have both forms of currency, we always want to use the currency that is most easily accepted in that situation. So we used up the euros before we used up anything else. But then let's say I got to the situation where I ran out of euros. If I'm out of euros and I want to purchase something, all I have are dollars. But the people that work in the stores and the shops, they don't take my dollars. So what do I have to turn around and do? Yeah, I have to try to find a way to exchange the dollars into euros. So the most common way to do that is to find some sort of a currency exchange or a bank and then ask them to convert my dollars into euros. Now, first off, that's going to take some energy on my part, just finding the bank and getting out of my way and postponing some of the activities that we were wanting to take part in that day to go transfer the money. But secondly, when I do find a bank and I get the conversion, do you think they're going to pay me an exact conversion? No, they charge you a fee. They have a conversion fee. That's how they make money. So in reality, even though I have a certain amount of dollars, I'm only going to get it converted to a certain amount of euros that's actually less than what it's worth because I had to pay the bank to do the conversion. So when it's all said and done, because the form of currency that I had in Europe in dollars wasn't the form that they accepted, I had to first convert my dollars into euros before I could actually use them. In the process, actually used up a lot of energy on my part and actually lost value of the money that I had in order to use it. This is exactly how your cells function, except instead of talking about dollars and euros, we talk about different forms of organic compounds, particularly things like carbohydrates and lipids. So carbohydrates are your actual currency form that the body readily uses. So at any given time, your body wants to use carbohydrates for energy, and we're going to get into the specifics of that reaction way at the end of the school year. But the actual process of making your energy for your cells and for your chemical reactions involves whatever it is you're eating to get converted into its basic form of carbohydrate. And that basic form is what we consider the monomer of a carbohydrate, or a monosaccharide. Okay, so what you see here at the bottom is a perfect example of a monosaccharide. The first one on the left is what we consider glucose. Glucose is probably the most common example of a monosaccharide that we're going to be using throughout the year, and it's definitely one you need to make sure you know. At the honors level, I expect you to know the chemical composition of glucose very well. If you look at the actual formation here of the structure, you'll be able to see the presence of one particular functional group that we spoke about before in bonding. If you'll notice that one functional group that I'm referring to is a hydroxyl group. There are quite a few hydroxyl groups in a glucose molecule, and each one of these, remember, hydroxyl has an OH. Remember, the O's have 6 valence electrons, so they require 2 shared bonds in order to reach that balance that they talked about. So every O that you see is going to be bonded to an H on one side and then a carbon onto the other, so that all of the O's are balanced. Remember, all the H's only need one more covalent bond to be stable, because they already have 1 valence electron. And remember, every carbon has to have 4 bonds, and you'll see every carbon here has 4 bonds extending off of them one way or the other in order to be balanced. You'll notice this oxygen here is in kind of a unique position because it's part of the loop, but it's not actually a double bond. It's simply 2 separate bonds, but they're both to different carbons in order to stabilize or become a basic compound that's stable like this. So this is what we consider a glucose molecule. It contains hydroxyl groups, which is that major functional group that we talk about here with carbohydrates, and it has the 3 basic elements of carbon, hydrogen, and oxygen. Now that's what a carbohydrate stands for. Carbo is carbon, hydro is hydrogen, and anything that ends in an ATE refers to oxygen. So a carbohydrate literally is carbon, hydrogen, and oxygen. And this is the most basic form of that. This is what we consider the monosaccharide, or glucose. So glucose is what we often consider as the basic monomer for a carbohydrate, which is this category of monosaccharides. Oftentimes, these are also categorized as sugars. So if you're ever having a basic discussion about types of nutrition and what you're taking in from your food, if you're referring to sugars, then we're typically referring to monosaccharides. Some other examples of these basic sugars, or simple sugars as you may hear them, besides this glucose molecule, is what you see up there above it, which is fructose. Fructose, you'll notice, is structured a little bit differently. The bonds are kind of extended differently, and one of the carbons, instead of being part of a ring, actually extends out more, so that it's more of a 5 carbon ring instead of a 6. And then the one at the very end is what we call galactose. Now fructose, as you hopefully can make the connection, is fruit sugar. So the kind of sugar that you would find in basic fruits, especially high concentration of fructose in sweet fruits, things like strawberries, mangoes, stuff like that, have very high amounts of fructose. That's the sugar that you see there, which is also a monosaccharide, or the monomer of a carbohydrate. And the one on the right there is galactose. Now if you hear galactose, hopefully you can make the connection of lactose and think about milk. So galactose is actually milk sugar, and the sugar that you would find in milks. And you can see that this structure, even though it looks different than the structure you see there for glucose, it's actually very similar. It's just it's drawn a different way. Rather than drawing out all of the C's, they simply have bends in the ring. So every time you see a bend in that 6-sided ring, each one of those represents a carbon. 5 of those carbons are there, then you have that oxygen in that one place, and then the carbon above it makes that 6th carbon. So these are all the same basic chemical composition in terms of numbers of carbons, hydrogens, and oxygens. As for glucose, and you will use that as a common example, if you counted up the number of C's that are there in that molecule on the left, you should count 6. We got 1, 2, 3, 4, 5, and 6. So in a glucose molecule, we have 6 carbon elements, or carbon atoms. Next up would be counting up the hydrogens, carbohydrates. So let's count the number of hydrogens. If you sat and counted them through, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So there are 12 hydrogen atoms in a glucose molecule. And finally, let's count up the number of O's, the oxygens. We have 1, 2, 3, 4, 5 here in the ring, and 6. So we have 6 oxygen molecules. So the chemical formula for glucose, and one that you absolutely need to make sure you remember for the entire year, is C6H12O6. And if you look at fructose and galactose, they have the same chemical composition of carbons, hydrogens, and oxygens. The things that are different are just how they're represented and how they're bended. Some of them bend upwards, some of them bend downwards, some of them aren't fully part of the ring, and so on. But it's the same basic element composition. So your monosaccharides and the basic examples I want you to remember all have the same basic C6H12O6 composition. Alright, so the major function of a carbohydrate, particularly these monosaccharides, is they are your body's energy source. They're your energy currency, the most immediate source of energy for your cells. So when you hear about different kinds of diets, I'm sure you've heard before that these simple sugars, if you take in simple sugars, they'll provide you with immediate energy because they're the exact form that your cells are ready to use. It's like having euros ready to go when you're walking your way through Europe. You have the exact form of currency that they want. And then if I wanted to use a different form of currency, I'd have to actually convert it first to euros before I can use it. And the same thing occurs here in your cells. Before your cells can use any other form of food besides these monosaccharides, it first has to be broken down into a monosaccharide and then turned around and used for energy for your cells. So this is what your body wants. If it has this and anything else, it'll use this first. And that's why a lot of diets are out there now that encourage lower amounts of these monosaccharides, or some of them completely eliminate them, which I would never encourage, because that's like saying go to Europe without any euros at all, which is probably not the smartest idea, because that means you're forcing yourself to convert these other things. You're not getting the biggest bang for your buck, basically, and you're forcing your body to work extra hard just to be able to get something done, which again is a way that you may actually lose some weight because you're pulling from other things, but in reality it's not efficient. You're not getting the immediate source of energy that your cells use, and if you kept that up for too long, your cells will start breaking down and really wearing down. So I'd never encourage completely eliminating it, but if you lower the amount of sugars that you're taking into your diet based on your activity, then you're not necessarily only using sugar as the energy source. If you're out of sugars, then your body is forced to resort to some of the other ones. And before we start talking about other categories of organic compounds, we'll stay within carbohydrates and talk about what happens if you're out of the monomer, which is the monosaccharide. So your cells use it in this form as the monosaccharide. However, if it needs energy and it's out of simple sugars like this, it'll pull to our polymer for a carbohydrate, which is what we consider a polysaccharide or a starch. So a polymer is just a combination of monomers. So if you look down here, you have 2 of the glucose molecules we've already talked about. So these are 2 monosaccharides already in their separate form. If your cells needed these as energy, they would take each of these individually and they would use it to make their own energy source. However, if we're talking about the formation of a polysaccharide, it's simply taking these 2 building blocks, these 2 monomers, and combining together. And this process of combining together is called dehydration synthesis. Now for honors students, I want you to be able to follow and understand the need for the types of bonds that you see here in order to keep the whole molecule stable. So if I were to simply combine these 2 together and put a bond between these 2 H's, I hope you would understand how that would make this molecule incredibly unstable, because each of these hydrogens can only make one covalent bond in order to stay stable, and they already have that covalent bond made with oxygens. So I can't actually make a bond directly between hydrogens here. And the same thing's true for that upper hydrogen on each side. If I combine those 2 together, again, you'd have no way of formation, or any kind of bond between any combination of these hydrogens would not work in terms of keeping it stable, because each hydrogen can only have one covalent bond, which they already have. So in order to think about how this molecule, these 2 separate molecules, these 2 monosaccharides, could combine to form a polysaccharide, in this case a disaccharide, which would just be 2, and still be stable, we need to start thinking about the reality that some things are going to have to be removed, some of these elements are going to have to go away, and there's going to have to be a bridge of an element that is actually successful with having two covalent bonds and stable with having two covalent bonds. So remind me, we have C's, H's, and O's. Which of the three elements actually wants to have two covalent bonds to become stable? Hopefully you remember it's the oxygens. So what's basically going to happen here is when these two combine, what's going to be remaining isn't any of these components except for one. So out of this whole group of four elements down here, there's only going to be one element remaining. And the other three are going to be separated out and producing another waste product besides this new polymer. So of the four elements, I'm going to keep one oxygen, and then I'm going to get rid of the other three elements in the form of a waste product. So I have two hydrogens and an oxygen getting released as a waste product. What product do you think I could make with two hydrogens and an oxygen? Water, exactly. So what we're left with, if we keep that oxygen there, we're going to be left with this water molecule that's going to be released out. And since that water molecule is going to be released out, it's going to leave that single oxygen to be the bridge that's going to hold this new structure together. So everything here becomes balanced, including that oxygen, which now has the two covalent bonds again that it needed and is a completely stable molecule. So this process of forming a disaccharide or a polymer from monosaccharides, or these monomers, is called dehydration synthesis, combining two molecules into one, and in the process losing a water molecule. This is what we call dehydration synthesis. It's called dehydration synthesis because if you dehydrate something, that means you're literally losing a water, which is what's happening here. And synthesis means to come together or to form. So dehydration synthesis is when two separate monomers combine to make a polymer. In the process, they lose a water molecule. Okay? Now once you have this polysaccharide formed, you can combine and make many components of monosaccharides together. Two together is what we call a disaccharide, but you can have very long chains of these monosaccharides, very long chains of glucose or of other monosaccharides together, and form what we consider to be polysaccharides. So for example, what you think of as table sugar, which I know I told you a sugar is a monosaccharide, table sugar or sucrose is actually a combination of a glucose and a fructose together through dehydration synthesis. So what we think of as simple sugar is actually a disaccharide, which is technically something you consider poly. But for the sake of our discussion, without it being the only exception, I want you to think of sugars as the monomer, the monosaccharide. So that's your immediate energy source, are the sugars, and that's what your cells are ready to use. That's the currency that they want. Now, if I had a chain of sugars combined together, again through dehydration synthesis, I'd have to lose a water molecule every time I had a space where two monomers combined together. So in this case, because I have four separate monosaccharides or separate glucose or monomers combining together here, where the two combine at any given place is going to be an area where I'm going to have to lose a water molecule in order for everything to stay stable. So in this molecule, when I combine the four together to make a polysaccharide, I'm actually going to lose three water molecules in the process, one in each space where two glucose molecules had to combine. This is the only way that the molecule will stay stable and stay balanced. So this is why we call this again dehydration synthesis, because we're losing water molecules as we're combining to make something bigger. Dehydration is losing water, and combining to make something bigger is what we consider synthesis. So here we are with this polysaccharide or a polymer. These are also known as starches. Okay, so if you ever refer to starches in your diet, we're talking about these long chains of monosaccharides. Now, this is not the form that your cells are ready to use. They need each one of these individually. But if you're out of sugars, the process of breaking this down and using it as an energy source really doesn't take all that much energy, and it's the exact opposite process of what we're seeing here. So it's something your cells can do fairly easily if they're out of sugars, right? So these starches are how your body basically stores your sugars. If you're not using them right away, it'll combine them and make these long chains of what we consider starches that are stored away in your body. For the honors kids here, if you have long chains of sugar stored in the human body, it's stored in the liver, and it's using certain hormones that we're going to talk about when we get into the endocrine system. That storage of long chains of starches in your liver is called glycogen. So the glycogen is what we consider long starches stored in an animal or a human, whereas plants store their long sugars in a different form. We'll be talking about plants quite a bit throughout the year. Hopefully you already understand that plants make sugar, so it's very common that they have a whole lot of sugar left over, or excess sugar. So those sugars get stored away through dehydration synthesis in these long starch chains, and in plants they're called cellulose. And it's that cellulose that turns around and gives plants their structure and firmness, and it's what makes up the cell walls of a plant cell as well as other major components. And hopefully you've heard cellulose before. So cellulose is the way that starch is stored in plants, whereas glycogen is how it's stored in animals. So if I wanted to use a starch as an energy source, first I'm pretty much going to be out of sugars. I'll use my sugar reserves first. If I'm out of that, then I'll simply have to take this polysaccharide and break it back into the monomer. And to do that, it's the exact opposite process of dehydration synthesis. We call this hydrolysis, and it's the exact opposite process here. I'm going to take the 4-part starch and separate it into 4 separate monosaccharides. And just like we talked about before, in order to keep everything balanced, we'd gotten rid of a water molecule anywhere where they combined before. So if I broke it apart and didn't add those elements back, then things would be unstable. I have to get things back to their original monosaccharide form. So in any time when I'm going through hydrolysis and breaking apart a starch, I have to make sure I add a water anywhere where there's this space between 2 monosaccharides when I separate them, so everything gets back to normal. So in this case, because it's a 4-piece starch or 4-piece polysaccharide, there would be 3 water molecules, 1 for every gap in between, that would have to be added so that they can separate and get brought back to normal. So hydrolysis, again, is the exact opposite process of dehydration synthesis. I call it hydrolysis for a few reasons. The hydro means I'm adding water, so hydro means I'm hydrating or adding water into the molecule, and then lysis means to separate. We're going to use that term lysis quite a bit throughout the year, so remember it. Anytime I refer to something lysing or going through lysis, that means it separates apart. So hydrolysis, you're adding water to separate. Dehydration synthesis, you're combining and dehydrating or taking water out in the process. And this is what your cells have to do if they needed to use a starch as an energy source, which again doesn't take a whole lot of energy. They do have to break some bonds in order to let this happen, but it's a fairly simple fix, and you get back to your monosaccharide form. So again, in terms of nutrition, carbohydrates are your immediate energy source, specifically the monosaccharide form or the simple sugars. So your body will use simple sugars first, and that's why, you know, if you drink something that's high in sugar, or you eat some chocolate or something like that that's high in sugar, you get a pretty quick rush. Or drink things like Gatorade and things like that that have sugar in them, you get a pretty big boost of energy fairly quickly. But if you're looking for long-term energy, any of you guys that play sports, they'll usually tell you, your coaches will usually tell you to eat a heavy meal of rices and pastas and things like that, which are starches, the night before, because by the time you wake up the next day, those starches are going to be ready to be broken down as your energy source, because a lot of the sugars that you might have eaten have already been used up. So your starches are what you're going to want to have in reserves, so that when your body starts getting really active, it can break apart the starch through hydrolysis back into these monosaccharides, and then each one of the monosaccharides can be used in your cells to make your energy. So just remember, the monosaccharide and the polysaccharide are the 2 monomer and polymer combinations of a carbohydrate. The major function is the immediate energy source for your body. If you have monosaccharides, you'll use them first. If you have polysaccharides, you'll use them next. And if you're out of both, then you're forcing your body to pull from other combinations of organic compounds that have to convert themselves ultimately into a monosaccharide form like these in order to even be able to function. And that process alone takes a whole lot of work and a whole lot of energy, so you don't get much efficiency in the process. So whatever it is you're doing in terms of your feeding habits and your diet, you absolutely want to make sure carbohydrates are a part of it. There's a lot that could be said about moderation in terms of how much carbohydrates you're taking into your diet, whether that be specifically in simple sugars or more complex starches, but I would never encourage anybody to completely eliminate it, because that's your immediate source, and there are multiple reasons you want to have an immediate source ready to use without having to put too much energy into the process. Alright, so I hope you got what you needed for carbohydrates. The next few videos will get into the remaining categories of organic compounds, and I'll see you guys next time.